Okay guys, so we did the easy electrostatics little introduction yesterday, so now looking at quantization and conservation of charge. First off, something very important, charge is a physical quantity, okay, so we're going to be doing calculations with it, so sort of just like wavelength and frequency from waves. Charge also has a number associated with it, a quantity associated with it. Its symbol is a capital Q and its units are a capital C in coulombs. Just quickly while we're on that, often your charge is not going to be measured in coulombs. It's going to be given to you in nanocoulombs or millicoulombs or something like that. Then you have to use that unit conversion table that I gave to you to change it back to coulombs. Okay, so for example, if they give it to you in microcoulombs, then you need to take that value. So let's say they say it's 3 microcoulombs. Then to change it to coulombs, you say, well, that means it's 3 times 10 to the negative, well, what did I say? Millimicro. So it's 3 times 10 to the negative 6 coulombs. So remember, you just stick that little conversion factor onto the end. Okay, now there are two major sections here for doing the maths. There's quantization of charge, and then there's conservation of charge. So quantization sounds scary, but quantization just comes from the word quantity, to quantify. So quantization of charge just means being able to actually measure it, being able to determine how much of it we have. Okay. Now, the overall charge on an object in coulombs, obviously we've seen this before, that depends on the number of excess or deficit electrons on the object. So if you have more electrons than you have protons, it means you've got excess electrons, and if you have excess electrons, it means your object will be negatively charged. And if you have a deficit of electrons, it means you don't have enough electrons, you've got fewer electrons than you have protons, and that will result in a positive object. Okay. Now, in order to determine what the overall charge in coulombs is, we have to know what the charge on one electron is. Now, one single electron, this is a constant value. It will be on your data sheet, and this is QE, and its value is negative 1,6 times 10 to the negative 19 coulombs. So the charge in coulombs on a single electron is negative 1,6 times 10 to the negative 19 coulombs. Okay. And then just in brackets underneath that, I've said we will be using scientific notation and unit conversions in this section a lot, so please make sure you're comfortable with it. Then, if we know the charge on a single electron, and we know how many excess electrons we have, we can determine the charge on our object. So Q, capital Q, is the charge on our object. Baby N is the number of excess electrons, and QE is the charge on a single electron. Now that makes sense, right? If we know how many electrons we have in excess and we know the charge on each of them, then we just multiply the two together and it'll give us the charge on our object. Now something very important, I want you to add this here. If you've printed this note, you're going to write it next to this little equation for me. So it says N is the number of excess electrons. So that means, and this is what you're going to write for me, if you have deficit electrons, N should be negative. Okay, so that's what you're going to write. If we have deficit electrons, then N should be negative. So excess electrons would be if N is a positive number. N refers to the number of excess electrons. So if I have 5 excess electrons, N would be 5. But if I have 5 electrons in deficit, i.e. I have 5 more protons than I have electrons, then N would be negative 5. Okay. So a little example here, we've got an object with a charge of negative 1,92 times 10 to the 17, and we want to know how many excess electrons our object has. Now it makes sense that our object would have excess electrons because the charge is negative. Okay, so that means I've got too many electrons. Now to determine how many excess electrons we've got, we can use our formula there. And remember, you always write your formula first, it's worth a mark. So we write our formula, Q equals N times the charge on an electron. We substitute in our values, and then we solve for n, and you'll see that n is equal to 120. This should always be a whole number. If you don't get a whole number, it means there's a problem with the question, because you can't split an electron. Okay, electrons are whole or solid whole objects. You can't get a fraction of an electron. Okay, then question 2, an object has 400 electrons fewer than it has protons. What is the charge on the object? So this 400, they've told us we've got 400 fewer electrons than we've got protons. This means that we have an electron deficit. And when you have an electron deficit, you express that mathematically by saying you have a negative number of excess electrons. So in this question, n is going to be a negative number because we have electron deficit. So that's what we wrote up here next to the formula. Okay, so n is equal to negative 400, and the question is to determine the charge on the object. So again, we're using Q equals n times QE. We substitute in what we know, which is the number of excess electrons, which is negative 400, and the charge on an electron, which is a constant value, which you will get on your data sheet, and you find the overall charge. Now note, I've put a plus sign in front there. Normally, obviously in maths, if you get a positive answer, you just write the number without the plus sign. When you are doing calculations with charge, I want you to please write the sign of your answer there, because the charge is either negative or positive. I want you to specify for me that that's a positive value. Okay, now just quick also up here, so that will be on your data sheet, and that formula will also be on your data sheet. Okay, now when we look at charges changing, so this was just looking at one object, stationary, nothing's happened, no electrons have moved, everything is sort of staying the same as it is. But we can get scenarios where your charge changes, so that means you've got electrons that have transferred, have moved from one object to another. Now, these equations are not on your formula sheet, okay? And for this section, you need to please remember that in order for charge to change, it's electrons that move. If electrons are added to an object, the object becomes more negatively charged. And if electrons are removed from an object, the object becomes more positively charged. Okay, remember that. So, there are two formula we can use here. Now, I hope we remember this delta sign. Delta means change in. Okay, so the change in charge on an object is equal to the change in the number of excess electrons multiplied by the charge per an electron. So if I tell you I've got 500 electrons that moved, that means the change in number of electrons was 500. I had 500 electrons moving from one object to another. Now, very important here, this delta n in brackets I've got here, negative if electrons are removed and positive if electrons are added. Okay, so there's two things now we have to worry about the signs. Over here with the n, okay, if n is an excess electrons, then n is positive. If you have deficit electrons, then n is negative. And then down here, if you've got a change in charge, if electrons are removed from your object, then that delta n will be negative, and if electrons are added to the object, then your delta n will be positive. Okay, and then there's a second formula here, and this formula is true for anything. Change in anything is equal to the final value minus the initial value. Okay, so change in charge is equal to the final charge minus the initial charge. Now be wary here, if you're subtracting initial charge and your initial charge was negative, then remember you're minusing a negative number, okay, which becomes positive. So make sure you use brackets when you substitute in here. Okay, and our example, we've got an object with an initial charge of 1,63 times 10 to the negative 16. It's gaining 6,300 electrons, and we want to know what is the change in charge. Okay, so change in charge means we're going to use one of these two formula. Now, how do we know which formula to use? We look what information was given to us. We've got the initial charge, and we've got the change in number of electrons. So far we could use either one of these formula, right? Delta n we have, and Q initial, we have. Now they want to know the change in charge on the object. So they want to know delta Q. So of these two formulae, the top one is actually the only one I can use, because if I were to use the bottom one, I would have to know what Q final is to substitute in there, but I don't know it. So I have to use the top one. because I know delta N and I know the charge on an electron. That's a constant value. Okay, so we're going to use the top formula. We write the formula because it's worth a mark, and we substitute in. Now here, when we substitute for delta N, we substitute positive 6,300 because electrons were added to my object. Okay, so over here in brackets, it's written there positive because electrons were added. Then the final charge, we substitute in and we calculate, and we find that the final charge, the change in charge is negative 1,01 times 10 to the negative 15 coulombs. So our initial charge was that, and our charge changed by that amount when we had 6,300 electrons added. Okay, then the second question, what is the final charge on the object? Well, now we can go ahead and use our second equation, hey, because we've just worked out delta Q and we knew the initial charge. They gave it to us in the question, so we can substitute in to find the final charge. Okay, so we're going to use the second equation. You write it down because it's worth a mark, and you substitute in. We've just worked out the delta Q is negative 1,01 times 10 to the negative 15. We were told the initial charge... Whoopsie, that's a mistake as well. Sorry, I'll change that before I send it to you. We were told the initial charge was, I'll change it in the question, negative 1,63 times 10 to the negative 16. And remember, we are subtracting now a negative number, so don't forget to put it in brackets. And we are going, so then it becomes plus, eh? So it's Q final plus that value, and we're solving for Q final, so we hop that one over and subtract it, and we get negative 1,17 times 10 to the negative 15 coulombs. Okay, so that's for quantization of charge and change in charge. Then conservation of charge, this one's a little bit easier. So for this, you're usually going to have a scenario where they say we've got two conducting spheres on insulated stands. They'll give you the charges on each. They'll say we bring them together, they touch for a little while, and then we pull them apart again, and then they'll ask you to determine the final charge on each. That's usually how this question will run. But anyway, let's go into the nitty-gritty of it. So conservation of charge, this in this blue blocky you have to know, please. It's a formal definition. So the principle of conservation of charge is that the net or total charge of an isolated system remains constant during any physical process. Okay, so if I have two objects with a charge each, whatever that total charge is, it doesn't matter what I do with those objects, as long as I keep the system isolated, the net charge will always stay the same. Okay, so if I bring two charged objects into contact and allow negative particles to transfer, then the total charge of both objects will be the same before as it was, it's the same afterwards as it was before. Okay, so this is going to be shown below. That's on the next page. We use conducting spheres. The reason that we use conducting spheres is because it allows for easy transfer of charge. We want them to be conducting. And our conducting spheres are going to be on insulated stands. The reason the stands are insulated is because we don't want charge to escape out of the bottom. Okay? We want the charge to remain in the spheres. We're keeping the system isolated. Now, if I have, what I'm going to do is I've got my two spheres. Okay, I'm going to bring them into contact and I'm going to pull them apart again, and we're going to look what's actually going on. So before we transfer charge, sphere A has an initial charge. We count the little pluses and minuses. Sphere A has an initial charge of -1, okay, because I've got 4 pluses and 5 minuses. Sphere B has an initial charge of -3 because I've got 6 negatives and 3 positives, and that means that my net charge is -2. Okay, in total I have 8 plus signs and 10 minus signs, so my net charge is -2. Remember that the net charge at the beginning was -2 because we're going to compare it to at the end, and it should be the same. That's what the principle of conservation of charge says, is that it should be the same at the beginning at the end. Okay, then we're going to bring these spheres into contact with each other, and what's going to happen is we're going to have electrons or negative charge transferring. And the direction that it transfers is your negative charge transfers from your more negative object to your less negative object. Now this can get a little bit tricky because what if both of your objects were positive? Okay, so you've just got to keep in mind that it's from the thing that's more negative to the thing that's less negative. So if we were comparing something with a charge of +4 with something with a charge of +2, well, plus 2 is more negative than plus 4 is. I know neither of them are negative, but in terms of which one is more negative, 2 is more negative than 4 is because it's less positive. Okay. So your charge transfers, your electrons transfer from the more negative to the less negative object, and they will keep transferring until your objects reach charge equilibrium. So that is, your objects will end up with the same charge. Okay, so your electrons are going to move until your two objects have the same charge and they've reached charge equilibrium. So for this example, sphere B had a charge of -3 and sphere A had a charge of -1. So in order for them to have the same charge, they must each have a charge of -2, right? If sphere B gives one electron to sphere A, then sphere B will now have a charge of -2. It's lost one of its negatives, and sphere A will have a charge of -2 because it gained a negative. Okay, so that means one electron moved from sphere B to sphere A in order for them to both have a charge of -2. Okay, then if we look after the transfer, so we pull them apart again, they've reached charge equilibrium. Sphere A will have a charge of -2, sphere B will have a charge of -2, and again our net charge, in total we still have 8 positives and 10 negatives, which means our net charge at the end is still -2, the same as before. So that's where the conservation of charge comes in. Okay, before and after the net charge is exactly the same. Then in this little blue blocky, this is where the formula comes in. So the charges in A and B are the same at the end. So they're both -2. And that value is actually the average of what their initial charges were. So if we say -3 plus -1, we get -4. Divided by 2, we get -2. Remember, that's how you calculate the average. Hey, you add together, divide by how many you have. So we'll have -4 divided by 2, which is -2. So the end charge on each of them is the average of their initial charges. So that's where we get our next formula, the conservation of charge formula, which says that the final charge is equal to the average of the two initial charges. You add them together, you divide by 2. And this formula is on your data sheet. Okay. Now, okay, so just a little summary of the formula for this section. So we've got a constant value, the charge on an electron, it is on your data sheet. We've got the quantization of charge. So you use it when you are determining the charge on an object or if you are determining the number of excess electrons on an object, and that is on your data sheet. And then when we talk about change in charge, these are unfortunately not on your data sheet, but that's just, this one is sort of very similar to that equation. It's just edited to have the deltas in there. So change in charge is change in number of electrons times charge on an electron, remembering that delta n is positive if electrons are gained and negative if electrons are lost. And then that the change in charge is the final minus the initial charge, also not on your formula sheet. And then our last one, the conservation of charge. When objects touch and charge equilibrium is achieved is when you use this one. So when you've got two spheres that touch and they say we've got a transfer of electrons. Okay, these are the questions that you're going to do. They start off nice and easy and they get progressively more difficult. So question 9, for example, that's a multi-step question. You've got to do at least, I think, let's quickly read it. You're given the charge on one, excess electrons on the other. What charge? Okay, so that's 2 separate calculations you have to do for question 9, actually. Okay, remember you might have to do unit conversions for this. Everything must be in coulombs, not microcoulombs or nanocoulombs or millicoulombs or anything like that. Make sure it's in coulombs. And yeah, good luck. Let me know if you struggle, please. And I will be able to help you. I will obviously also send you the memo. We will go through this when we get back to school because I know this is quite tricky. People do tend to struggle with it. But please just try your absolute best. Let me know if you get stuck.